back to the next lecture of this afternoon session. So it's given again by Raffaello Bianco, who is our expert on this thing. And now I think that this lecture is important because it's here where we really calculate physical phonons. This is where the physical phonons come into play so far. So far we have done thermodynamics, and in this moment, right now we will also do dynamics. Okay. So yeah, so I think that Rafael, the floor is yours.
Okay, thanks, Jan. Okay, so yes. Okay. So where we arrived this morning. So we arrived to this object here. So this generalized dynamical matrix given by the second derivative of the free energy with respect to the average atomic position. Okay. This is our first step, let's say, to generalize what phonons are when we consider free energy and quantum effect, thermal effect, and so forth. However, as we saw, at the end of the day, we just had numbers, real numbers, obtained by diagonalizing this object. But we know that true phonons are vibrational excitation of the vibrational collective excitation of the vibrational degrees of freedom in a crystal, and these excitation have not an infinite lifetime, so they decay. And so for sure we cannot see this if we just consider eigenvalues of a real symmetric matrix. So we have to go on. And essentially, we need to consider a dynamical theory, because what we did this morning was everything was static. So we need to introduce dynamical effect when we study the vibration of the atoms. So just a recap. So as we have seen already, the self-consistent harmonic approximation is essentially an R3-Fock, but for phonon. So what is R3-Fock? We essentially use a vibrational method for the electronic free energy, and we use this approach in order to describe a system, the electrons, fermions, which are interacting. We study this system by introducing effective non-interacting electrons to include somehow the interaction. This is essentially what you are doing in the SCHA. So we are introducing effective non-interacting bosons in order to include somehow the interaction between the real phonons, the harmonic phonons, which is what we call anharmonicity. Okay, so as you can see, SCHA is really an R3-Fock for phonons. And at the end of the minimization, we obtain this Hamiltonian here, which is our, let's say, effective harmonic Hamiltonian. So it's the best harmonic description of a system which is not harmonic. So this is the best way to describe an harmonic system in an harmonic way. By using this Hamiltonian, so we can define somehow kind of phonons, right? Just like in R3-Fock, you use the Slater determinant to define these fake Fermi, these fake electrons. In the same way, you can use this Hamiltonian to define somehow boson quasiparticle that mimic some way the phonons. So we are replacing the harmonic phonons with another kind of quasiparticle, which are these SCHA quasiparticles, which are kind of dressed harmonic phonons, okay? And here I'm just using here this line, with this line to describe the propagator of these two particles, okay? These two different quasiparticles. So what we are doing, we are replacing up to now the harmonic phonons with these SCHA quasiparticles, and this is the relation between the two particles, okay? So if this is the SCHA, the propagator the green function of the SCHA quasiparticle. This object is given by a series given by this harmonic propagator. So as you can see, the SCHA propagator includes somehow part of the anharmonicity, because here, as you can see, we have interaction between harmonic phonons. So the SCHA propagator by itself already includes somehow part of an anharmonicity. However, even in this way, okay, we still have that the SCHA quasiparticles are not interacting. So the SCHA propagator includes somehow the anharmonicity, but at this level, the SCHA particles by itself are not interacting among themselves. So this is the situation. If this is the true Hamiltonian of our system, we can write the true Hamiltonian of our system as the SCHA Hamiltonian, so this effective harmonic Hamiltonian that we have defined at the end of the minimization of the free energy functional, plus this object here, which is simply the difference between the true ionic potential and this SCHA quadratic potential, okay? So if you look at this Hamiltonian, you can see that this Hamiltonian here, the SCHA Hamiltonian, describe these SCHA quasiparticles that are not interacting. But this term here actually introduces the interaction between these particles. So this is what we have to do now. We have to somehow to understand how this term affects the propagation of the SCHA quasiparticle and introduce the interaction. In order to do this, it has been developed a very elegant theory, the time-dependent self-consistent harmonic approximation, because this is a typical time-dependent problem. So we want to understand how the propagation, how the vibration described by this SCHA quasiparticle propagates in time. So in order to do that, we need a time-dependent theory. Okay. I won't give you details about how to derive this theory, but I will give you, so I will try to convince you why the results that I'm going to show you somehow are consistent and are correct. So the main concept that I want to introduce, so is the green function. So the green function of the displacement of the atom. So this is the displacement correlation function. So U here is the displacement of an atom from the equilibrium configuration at time 0, and then this is at another time tau. Here I'm using a formalism of this is the time ordered product. So more or less, the ones of you that are that know more or less the green function theory will recognize this object here. So this is the green function. And then by using the Matsubara transformation, I can go from the time variable to the Matsubara frequency variable. And then I can do an analytic prolongation to go from the imaginary axis, where I have these Matsubara frequencies, to the full complex plane. I'm telling you this just to fix the notation, okay? So this is the main object, the green function in the Matsubara formalism. So what do we have now, up to now? We have the non-interacting SCHA phonon that propagates without interacting. And what is the green function of this SCHA phonon? Is this object here? This essentially is totally analogous to the green function of the harmonic phonons. But here, instead of having the harmonic dynamical matrix, we have the SCHA dynamical matrix, okay? But for this is identical to the standard harmonic phonons green function. And this, as you can see, this from this expression actually, you can see that these are non-interacting particles, because here you have this D is a self-adjoint operator, so it's a real symmetric matrix. Okay, so we want to go from here now to the true SCHA phonon propagator that describe particles that are interacting. Okay, so this is this full wiggled line. Okay, so the question is now how is done this G. Okay, And all the properties about lifetime of phonons aligned with spectral properties all of them are encoded in this included in this object. Okay, so the main goal now is to derive an expression for this G. So the best way to show you what is the result is to use a pictorial description, which is the description in terms of the Feynman diagrams. So what is the situation? So here I have the green function of this, the full green function of the vibrational collective excitation of the system that includes some interaction. And this can be expanded in this series. Okay, so we have here the SCHA quasiparticle non-interacting propagator. Then there is this bubble here, which is called self-energy, which actually it includes an infinite number of diagrams that describe all the possible interaction, connected interaction of the SCHA phonons among them. Then you have also this term here, so two of these self-energies, where you have only what we call connected diagrams, and so forth. So 1, 2, 3, an infinite number of this diagram. And you can sum up this infinite series in this way. I don't know if you are familiar with this. I can also use the, I don't know, if I have time, I can also use the blackboard. So essentially, the situation is you have one free propagator, then you have a self-energy like this, then you have another self-energy like this. So if you, let's say, and this is the full propagator. And now if you can take this part, just on the right of this part here, and you can see that essentially if you consider an infinite number of these terms on the right, you are recovering again the same object. That's why you can write in this way. If you substitute the place of the full wiggled line, the same expression over and over again, you recover the full series, okay? And this is what we call a Dyson equation. So if this is the graphic expression of this equation, this is just the same object but written as let's say an operatorial equation or a matrix equation. Okay, G0 and this one. So these are not simple products. These are matrix product, or if you want, products between operators. Okay. So so we have reduced the problem of finding the full green function to the problem of finding the self-energy, this pi. So it can be demonstrated that this pi diagram, so the self-energy, is given by a sum of diagrams done like this. So what I have here, this wiggled line here is just the SCHA quasiparticle propagator. This fake boson that we obtain from the effective SCHA Hamiltonian. Okay, so we have just one of these, and this point here is what we call a third order vertex, because as you can see, we have three lines that end up in this vertex. Here we have a third order vertex here, then a fourth order vertex here, you see, because you have four lines that are entering this vertex. And then again, three lines here, so on and so forth. So how is done this vertex in practice? It's given by this object here. So this vertex here is given by what I have defined this morning. Again, the same object appears now. So we have the third order force constant matrix. You remember this was given by the average of the third order derivative of the potential, and the average is done with respect to the SCHA density matrix here, divided by the masses, and this object here is this vertex, this third order vertex. And for the fourth order vertex, we have a similar expression. So now this vertex is given by this object here, where pi to the 4 is given by this. Okay, so maybe you are recognizing that somehow we are recovering something similar to what we have already obtained this morning when I spoke about the Hessian of the free energy. This is not by chance. As we will see, there is a strong connection between the Hessian of the free energy and the self energy. Okay. So let's see now. Let's translate again from what we go from the diagram to from this pictorial description to something more, let's say, analytical. Okay. So how is done this object here? Okay. So here on the left we have one third order vertex here. Then we have this double scalar product because this is a 3-order tensor, so this has 3 indices, and this is the lambda, which is something similar to the lambda that we have seen this morning. Now I will give you the exact expression, and here on the right we have another third order vertex. As you can see, it's really the description of this object here, and as I told you this morning, this lambda actually is given really by this this kind of polarization diagram. So what is the situation that we have here? So we have something like this. So when you want to write an analytic expression for this object, and you use the Matsubara formalism, you have here something like an object like this, which is the energy of this this incoming particle written using the Matsubara frequency here, and then this split, and you have must fulfill the energy conservation. So this becomes something like this, and minus another variable, L, for example. Here you have E, L, and then again here, N. And then you sum over all the possible values of this L. So what are you doing, essentially? You have a particle with a certain energy, then it splits in 2 particles with different energies, but the sum of the 2 energies must give the energy of the incoming particle, because there must be energy conservation. So if you consider all the possible diagrams by changing the value of L, so you do something like the propagator, the product of these 2 propagators, G0, because this is the SCHA non-interacting Green function. So you have something like this, E omega L, and then you have the product, this other down here, G0 E omega N minus E omega L. And if you do the sum of this object, okay, essentially you obtain that lambda. Okay, what is the difference between what we did this morning? So this is the lambda that you obtain. This is the analytic expression. What is the difference with respect to what we did this morning? That now I have a zeta there. Okay, this morning I had a similar expression, but instead of zeta, I had a generic zeta. I had zeta equal to 0. Okay, so if I put in this expression here, zeta equal to 0, I exactly recover the lambda that I used this morning to write the expression for the free energy Hessian. Okay, so the difference essentially is that instead of having all the possible energies here I have 0. This is the difference. Okay, that's why another way to say that the theory that I described this morning was static. Okay, there was no an energy propagation inside. It was everything fixed. Okay, but this sense is static. Okay. So stop me if something is not clear. So, so this is lambda at the end of the day. So lambda is given by this diagram here, summing over all the possible energies in which I can split this particle. And this is this term here becomes this object here, okay? This is what we call the self-energy in the bubble approximation. If we just discard the other terms, as this morning, as I told you this morning, often we can discard the fourth order vertex, the fourth order derivative. If you do so, for example, in this case, you obtain, you just reduce, you just approximate the self-energy just with this diagram here, which looks like a bubble. That's why it's called the self-energy in the bubble approximation, okay? Let's now look at this other diagram, for example. Now, let's say the logic is the same. We have a third order vertex, so D3. Then we have these two free propagators with all the possible energies. And then when I consider all of them and I sum the amplitude altogether of all the possible processes, I obtain this lambda here. Then I have a fourth order vertex. Then again, I consider all the possible two lines here, and I obtain lambda again, and then a third order vertex here. Okay, so this other diagram is translated in this form here. Then I can also consider this, for example, it's the same. D3, lambda. D3, D4, lambda. D4, lambda, D3. Okay. And so forth. So essentially, I am obtaining a geometric series. Indeed, I can just write in this form, as you can see. If you consider this series and you expand, you make a Taylor expansion of this object, at the end you exactly recover this. Okay? So this is the expression of the free energy in the SCHA formalism, in the SCHA approximation. Okay? As you can see, essentially all the objects that are here are the same object that we needed to compute the Hessian. So it's something that is really computable, and so going from the static theory to the dynamical theory, from this point of view, is not more expensive, let's say. Everything is already available. Okay, so what I did here, I want to make clear the connection now with what I have done this morning, okay? So let's now consider, instead of a generic zeta, what is zeta essentially? I said it comes from the analytic prolongation, blah, 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 but essentially it's the energy, okay? If you want, you can think about this zeta as a tag that indicates that there is an energy in this situation, okay? So when I consider a static situation, so I put zeta equal to 0. And if you remember this morning, this was essentially, if you, instead of a lambda with 0, you put lambda, because I have shown you it's the same object. If you remember, this is what I showed you this morning, is the free energy Hessian. Okay, so I have recovered now, with zeta equal to 0, the free energy Hessian. So essentially, the free energy Hessian can be written in this very expressive form. So the free energy dynamical matrix, which is the free energy Hessian, is given by the SCHA dynamical matrix. So the dynamical matrix of the SCHA quasiparticles non-interacting that comes from the SCHA effective Hamiltonian, this D, plus the self-energy at static level. So this is the situation. This is the full Green function. This is the SCHA phonon Green function. This is the self-energy. This is the Dyson equation that we have seen. And G of the phonon, the SCHA phonons is given by this. And the full instead G zeta is given by this object here. Essentially, you just, to go from this formula to this, you just have to make a bit of algebra, just going, just putting this on the left, and then dividing. Of course, Here I'm dividing, but this is not division by numbers. These are inverse of operators, okay? And if I consider the static, so static expression, so I put zeta equal to 0, this is what you obtain. This is what we call the static limit. And as I told you, D plus the self-energy evaluated for zeta equal to 0 is the free energy Hessian. So I can write in this way. So this is essentially the more or less the whole story about the, please.
But in the last formula, if zeta equals 0, why do we maintain the zeta square term?
Because this is essentially the content of the static approach. You keep the fact that there is a zeta in the essentially like here. So the static approximation, if you want, is that you say that the free energy, that the self energy does not depend on the energy of the object. It's fixed, and it's fixed at the static value. Okay, but you keep still at zeta because you keep also here. So the zeta is necessary in order to have a dynamical theory. But considering a static situation, static approximation for the self energy means that you are just blocking this object here. Okay. So this is the static limit. Just a few words about the static limit. So this is the static limit. So G, the full green function evaluated for zeta equal 0 here for just for the self energy. So what we have seen. So in the static approximation, is essentially the situation is still described. So even if you look from the point of view of the green function, it's still described just by a real symmetric matrix, this D of F. And therefore, what are the, when you study the dynamic of a quasiparticle by look at the green function, when you study a collective excitation of a system, and you consider the green function, what are the energies? The energies are given. What are the energies of the excitation? The energies are given by the poles of the green function. Okay, and what are the poles of the green function in this case? The poles of the green function are given by the eigenvalues of this, the square eigenvalues of this D of F. Okay, so essentially, the result that you are obtaining is was expected. It was it's a natural because what does this mean essentially? We say we say that if the green function has a pole at 0 energy, what does it mean? It means that we have a phonon with an energy close to 0, which means that we have a softening, which means that the system is unstable. And when the system is unstable, we have seen this morning, this is equivalent to say that the free energy has a 0 eigenvalue. And essentially, with this formula, we are recovering these two point of view, okay? So if this object has a pole at 0, this means that we have a phonon that is becoming soft, so the system is unstable. And this is equivalent to say that the free energy Hessian has a 0 eigenvalue. So essentially, we are looking at the structural instability from two different, in a sense, point of view, which are complementary. Okay, so up to now I have spoken about the green function. So I have spoken about the dynamical SCHA, the dynamic SCHA. Okay, but what is the real object that actually we need to compute quantities that we can compare with the experiment? Essentially, the main quantity is the spectral function. This is the definition of the spectral function given by the green function, the single particle green function here. So essentially, for the maybe you know the theory. Essentially, this is what we call the retarded green function. So essentially, we have the green function. As I told you, we started from the green function defined on this imaginary axis. This is the real axis. This is the imaginary axis, and these are the Matsubara points. Okay. Then we made the analytic prolongation, and so we went from here to here. So these are called G. These example, the Green function defined for the different Matsubara frequencies, which are imaginary, high frequency. Then we prolong to the full complex plane, and then we can go from above and from below here to the real axis, okay? In general, the imaginary part of this operator, when we go to the real axis, is different depending if we go to the real axis from above or from below, okay? When we go from above, we obtain what we call the retarded Green function. And so this is the meaning of this object here. Omega here is a real number, and I'm saying that I'm going to this number from above. If you consider the trace of this object, okay, it's an operator, it's a matrix, and then you consider minus the imaginary part, you obtain what we call the spectral function. What is the spectral function, essentially? It's the energy spectrum of this excitation, of this collective excitation. This is the object that actually you measure when you do an elastic scattering experiment, for example. So you do an experiment when you use neutrons or X-ray, and then this scattering is inelastic, so part of the energy is lost, is gained. And by analyzing the outcome, you recover the energy spectrum of the excitation of the crystal and the vibrational collective excitation of the crystal. And this information is the one encoded here, okay? So what is, up to now, I have spoken about the Green function of the SCHA phonons and the full Green function. Now let's see what happens when I consider the corresponding spectral function. So the spectral function of the non-interacting SCHA quasiparticle, so which as I told you are the Green function is given by this object here, which is the Green function, for example, is identical as the Green function of the harmonic phonons, but instead of having here the standard harmonic dynamical matrix, here we have the SCHA dynamical matrix, effective dynamical matrix, okay? When we do this minus imaginary trace of this object, essentially, we see that the spectral function is given by sum of Dirac delta, okay? So how is given, how is done this spectral function? So essentially you have that if this is the energy, you have delta x here corresponding to the eigenvalues of this square root of the eigenvalues of this object here. So the frequency, okay? So what means that these spectral peaks are Dirac delta, which they have zero width. What does it mean that they have zero width? It means that they have infinite lifetime, because the concept is, if you want, you can think about the Heisenberg uncertainty principle, the uncertainty on the energy times the uncertainty on the time is h bar over 2, bigger equal to. So the bigger is the uncertainty on the time, the smaller is the time an excitation survives. So if we have an Hamiltonian and we take the eigenstates of an Hamiltonian, we have the energy is fixed, so we have no uncertainty about the energy, and indeed this state lives forever. But when we consider a situation where instead we don't have exact eigenstate of an Hamiltonian, like when we consider a full interacting situation, we will have, instead of very narrow zero width peaks, which means perfect eigenstate, we will have a width, okay, here, which means that the system, this excitation has a finite lifetime, okay? But in this case, as you can see, we have Dirac delta, so this is not the case. In this case, as expected, since the SCHA quasiparticles are not interacting, they live forever. They are eigenstate of the Hamiltonian, and they live forever. The same is if we consider the spectrum of what I've called the static approximation. This is the green function, and this is the green function in the static limit. And as we have seen, this object is just the free energy dynamical matrix. And again, since when you consider the imaginary part of an object like this, where here I have just a symmetric real matrix, with a bit of mathematics, you can see that if you do the imaginary part of this object here, it's just a sum of Dirac delta, okay? So again, when I consider a green function that is done in this way, where this is a real symmetric matrix, I have particles that live forever, okay? But how is done our true green function? Our true green function is done in this way. I don't have here pi, the self energy fixed at 0, but I have a pi that depends on the energy. So if I put the correct expression of the self energy, this is what I've done. So the true spectral function is given by this object here, okay? And indeed, as you can see, for example, from this picture here, this is actually what we see in a real experiment. We don't see this, what is this experiment? This is the result of an X-ray scattering experiment. So each line is a different point of the, say, of the Brillouin zone, where we have probed the vibrational excitation with that modulation in space, and we have measured here the energy spectrum. And as you can see, we have peaks which have a finite width. They are not they're not zero width. So they are particle excitation that have a finite lifetime because they decay. And they decay because they interact among themselves. So this is the full formula, okay? And in principle, this is something that the SCHA can compute. So essentially, the SCHA, as I told you, we can compute D, of course, because it's just the SCHA dynamical metric. We can compute pi, because we just need third order and fourth order averages. Then we can compute this object, and then we can invert this object here. Then we can make the trace, the imaginary part, so we can compute this object here, and have the full spectral function. So we can compute something that can be compared with the experiment. But there are also approximations that we can do that on the one side allow us to use less computational resources, and on the other side help us in understanding, say, some feature of some aspect of the results. Okay. The main, let's say, approximation that we can do is to neglect the mixing between different modes. This is what we call a no-mode mixing. What does it mean? It means that when we consider the interaction among different SCHA quasiparticles, we somehow neglect the possibility that a phonon, a SCHA phonon of a certain mode becomes another mode mu. This is in principle possible, but we have seen that this is very often a very good approximation to neglect this possibility, which means essentially that if we consider, now I'm writing explicitly the self-energy as a matrix, it means that if I write this matrix, this operator, in the basis set of the SCHA mode, this is a diagonal matrix. This is essentially what I am saying here. As I told you, this is usually a very good approximation. However, have a look at this paper where we show a case where this is not true. So what happens when we use this no-mode mixing approximation? Again, we can write the spectral function as a sum of a spectral function for each mode. And for each mode, we have this expression of the spectral function, where this zeta here is this object here. So this is the square root of this is the squared SCHA, what I call the SCHA frequency. With this I mean the eigenvalue of the SCHA dynamical matrix. So the SCHA force constant that I obtain at the end, because maybe it's confusing a bit. So when I say this omega mu, I write this here. So you do the SHA, you do the minimization. At the end of the minimization, you end up with a certain phi here, which describe the effective harmonic potential at the end of the minimization. If you divide this by the square root of the mass, MA and B, for example, AB, this is what I call D SHA AB. And if you diagonalize this object, you obtain what I call here omega mu.
We call it auxiliary.
Yes, we call sometimes call it auxiliary. So these are, as I told you, these are not real phonons. These are just these effective phonons, just like in the Sladen determinant in the Hartree-Fock are just effective electrons, okay? But these are not the true phonons. The true phonons at the end are given by the spectral function, okay? That is the real information that you have to compare with the experiment. This is an auxiliary quantity, so we can call it auxiliary phonons, okay? But this is the frequency that I'm writing here, okay? And this is the self-energy written just mu and mu, because I'm neglecting the mixing between different modes. So let's look at this expression. Before doing that, I want to stress just a point. So if I neglect this mixing, I can still keep the concept of mode. Because in general, if I consider the full this full expression here, I cannot speak anymore about single modes. Everything is mixed. I have here an imaginary part of a trace of an operator. Everything is mixed. Okay, I don't have any more different modes. Okay, everything is together. But if I exclude the possibility that different modes couple through the self-energy, then I can still keep alive the concept of mode. And so I have that the full spectral function is given by the sum of a spectral function over the single modes, okay? So from this point of view, that's why this approximation is interesting. Not only because it makes easier to evaluate this expression, because I don't have any more to invert a giant matrix. Okay, this is easier to compute, but also because in this way I can see the effect of an harmonicity on the single modes. Okay, so that's why also if you analyze this quantity and if it makes sense to neglect this object, that's why it's interesting to study the spectral function in this form. Okay? So let's have a look at this object here. So this looks like a Lorentzian. If you know, the Lorentzian is an object like this. So a Lorentzian is something like this. So we have here omega is the variable, and this bold omega is the center of this curve, this Lorentzian, and this gamma here is the half width at half maximum. So if you consider half of the maximum of this curve here, the width is given by twice this gamma here. So this is what is called a Lorentzian. Okay? Now this is quite similar to a Lorentzian, but as you can see, I don't have here a number, a fixed number. I don't have a number. I have a function, because also this numerator here depends on the variable. And also here, the center is not a fixed number like here, but it's something that depends on omega. So it's not a real Lorentzian. It's something similar to a Lorentzian, but it's not a Lorentzian. However, there are cases when we can approximate this with a true Lorentzian. Okay. Sometimes we can approximate the previous expression with something like this, where this center of this Lorentzian is given by this self-consistent condition, okay, where zeta is the object that we have seen before. Sometimes when you solve this self-consistent condition, and then you use this number to evaluate this gamma here, you obtain a function, a Lorentzian function that is pretty similar to the true. It's not given, but when it happens, we say that the quasi-particle picture is correct. Why I'm saying so? Because essentially, I don't know if I will figure later, maybe later, yes, but I can start saying something. Because essentially, what is the situation? So I'm starting with this Dirac delta that correspond to different eigenvalues of this SCHA dynamical matrix. And then at a certain point, I work on the spectral function, including the interaction between this SCHA quasiparticle. And the spectral function is not anymore given by these peaks like this, but it becomes something like this. If the Lorentzian approximation is good. So I still have something that resembles sort of the Dirac delta, but now as a width and as a definite energy, the center, okay? So what does this mean? If the spectral function at the end of the calculation looks like something like this means that the quasi-particle description of the collective vibration is still a good concept, because I can interpret the energy of this collective vibration, excitation of the vibrational field, as particles, which have an energy, and I have also a lifetime. Okay. So if I can do this, this means that I can still speak about quasi-particle. But there are cases, and I will show you an example later, where this cannot be done. In that case, we have to say, okay, the quasi-particle picture is not appropriate anymore. So the concept of a quasi-particle, in that case, is not valid anymore. Okay. So as I told you, in principle, you should, in order to give the best Lorentzian approximation to the spectral function, you should solve this self-consistently. But there is very often a very good approximation that we call one-shot approximation. Is here, instead of solving this thing self-consistently, we just put here the SCHA frequency. Okay, and then we use this object, and also we do the same for gamma. Often, quite often, when you do this approximation, you obtain a Lorentzian which gives a good approximation of the spectral function. There is, in particular, a case that also allows to make an approximation, is when the self-energy is much smaller than this square frequency here. In that case, you can just do a Taylor expansion at the lowest order, and you can see that this condition simply becomes this. So in this case, essentially, we are recovering Lorentzian by applying per lowest order perturbation theory to the spectral function, okay? But this is just a spectral function on this, this is just perturbation theory on this spectral function. Doesn't mean that you are doing perturbation theory on an harmonicity, okay? This is just perturbation just on this expression here. Okay, so in summary, what is the situation? So, first of all, as I told you, we have these SCHA form quasiparticle, which are, this is the spectral function of this SCHA form quasiparticle, which is just a Dirac delta, so just a line, with an infinite lifetime, because these quasiparticles do not decay, because they don't interact. Then I consider the non-mixing mode approximation. I evaluate, for example, I evaluate the spectral function, and let's assume that we can approximate the single mode spectral function with a Lorentzian. So this is what we obtain. So instead of having an excitation here with the Dirac delta, we have an excitation here given by this the spectral function given by this Lorentzian with a certain width and energy. Okay. So this is when the quasi-particle concept is correct. But sometimes what can happen, instead of, we compute the full spectral function and we find something like this. I'm still in the no-mode mixing approximation. So I'm still speaking about the spectral function of a mode, the mu mode here. But I'm not able now to say that the Lorentzian approximation is valid, because because in this case, for example, the spectral function is something like this. So I have something here, which in this case I could say it's a shoulder deviation of the spectral function from the Lorentzian spectrum. Okay, this means that essentially I don't have anymore a quasi-particle. Okay, because it's not really possible to say where is the energy. Okay, maybe this is not very extreme. In other cases, it's even more extreme, the picture. But when you start deforming this Lorentzian spectral function, you end up with a situation where you cannot say anymore what is the energy and what is the lifetime of that quasi-particle. Okay. So, so this is the situation. I do a summary. So we have, first of all, what is the physical object? The physical object are the collective excitation of the vibrational field of the atoms in the crystal. What is the quantity that characterizes this excitation? The energy of this excitation. This is so the energy spectrum. That is the quantity that we probe when we do inelastic scattering experiment. When we have we have seen that with SCHA we can compute the energy spectrum, and when the interaction between the single SCHA quasi-particle can be neglected, so what I call the no-mode mixing approximation, I can describe the full spectral function as the spectral function, as the sum of the spectral function of the single modes. So this is in general not true, but many cases we can do that. And also I've seen a case when the self-energy of this SCHA phonon is small enough that not only I can say this is the spectrum of this mode, this is the spectrum of this mode, this is the spectrum of this mode, but for each of these modes, I can also say the excitation of this mode can be described as can be seen as a quasi-particle with a certain energy and a certain width. So we have different level of, let's say, or linear approximation, or the full spectral function, or the spectral function of single modes, or even the spectral function of single modes can be described as a quasi-particle. So there are 3 steps, let's say. Okay, so far I have shown you the formalism in the real space, because the self-consistent, the SCHA is first of all a supercell method, but then by exploiting the crystal lattice symmetry, we can then recover also the description by doing the Fourier transform. So we have also the quantities with a label that indicates the modulation, the wave modulation in the reciprocal space. And so I am here the SCHA dynamical matrix depending on Q, the corresponding omega. Then I have the free dynamical matrix Q and the corresponding eigenvalues big omega. And then I have a spectral function. It also depends on the energy, but depends also, in general, they are not coupled. So for each Q, we have a different spectral function. And if we are, as we have seen, if we are in the Lorentzian, if we can apply the Lorentzian approximation, then for each Q, we have also quasi-particles with a certain energy and a certain bandwidth. So, what is the phonon spectrum then? Okay, so as we have seen this morning, in principle, I can just take the Hessian free energy, I can diagonalize it, and I can plot this quantity. This somehow is a first, let's say, it gives you a first glance to what are the phonons, okay? Especially when at the low frequencies, because of course, if the frequency is very low, it's going to 0, and so it's close to the static approximation where the result is exact. So when you plot this object here, so the eigenvalues of the Hessian free energy, in general at high frequencies they are not they don't even are similar to the true phonon spectrum. But if you go at the low energy, at the low frequency, this can be quite similar to the correct phonon dispersion. But this is in principle the correct quantity to describe phonons. as I told you, of course, this is true only if the quasi-particle concept is correct. When you plot phonon dispersion, you are assuming that there are quasi-particles, okay? So quasi-particle can describe our excitation. And in this case, so this is the phonon dispersion. This is the center of this Lorentzian, and the plus minus the line width, because essentially this is you can consider this as the energy uncertainty of the phonon frequency. So this is essentially what I've showed you this morning about H3S. So we made the full calculation in the Lorentzian approximation. The blue line is the center of this Lorentzian, and this lighter blue gives the energy width, okay? So as you can see from this picture, for example, the line width of the high frequency mode, the high frequency phonons here, is it's very big, whereas for the low frequencies, we have quasi-particles which are long lasting, okay? Because they have a very small, here you cannot even see it, okay? Okay, so this is an example where the quasi-particle concept is correct, because we tested it, and so we saw that we can plot something like this is meaningful. So we have energies and we have line width of quasi-particles. But for example, here, this is a case where the quasi-particle concept does not apply. This is tin telluride at 300 Kelvin. So here, what I'm plotting here I'm plotting the spectral function in color code, okay? So essentially, what is the spectral function is something like this. Q, and this is omega, the energy. So essentially, for each value of Q, which is on the path on the horizontal axis, and for each value of the energy, which is here on the vertical axis, I have a value, and then I'm plotting this value in color code, okay? So in general, this spectral function is essentially quite similar to, it's well described in general by a quasi-particle, because it's very localized here. So we have a certain width, but it's a quasi-particle with a certain energy and a certain width. The problem is here in gamma, as you can see. And you can see better that the problem is gamma by looking here at this picture here. I have taken here the vertical axis here. So I have three modes here, 4, 5, and 6 in gamma, which are the optical one. Of course, the acoustic one is meaningless. So the mode 6 is very Lorentzian. So essentially we have a peak with a certain width and a certain energy. But here, if I plot the spectral function in the Lorentzian approximation, this is what I obtained, these two peaks. But the true spectral function is this, sorry, it's the opposite. If I consider the Lorentzian approximation is this red thing here, oops, which is a double degenerate, and this is very, but if I plot the true spectral function, I have something very different. So in this case, we can safely say that the modes 4 and 5 are not well described by the quasi-particle concept. We don't have a single peak with a certain energy and width. We have something more strange. And this is what we see. This is the spot here is what we call in general a satellite. So something that deviates from the spot that deviates from what you would expect if this were a simple form of dispersion. Okay? And as you can see, it's also a very good agreement with the experiment. The experiment is given by these black dots. So here you see a satellite here, and the satellite corresponds to this. Okay, this is all. Yes?